Hello, everybody. We're going to be going over Physics 2, multiple choice question A, question set A for Unit 5, which deals with magnetism. Okay, so here we have something called a CRT, a cathode ray tube, which is a device that projects a beam of electrons onto a screen that is treated to show where the beam strikes. And so the figures show a CRT screen and a dot where the electron beam is directed out of the page. And so that's going to be here. I kind of reformatted it. And so the electrons are going to be coming from the back over here, and the electrons are going to be flowing with a velocity in this direction. Also shown is the location where a compass can be placed to investigate the magnetic field produced. And the first question here is, a compass is placed directly below the electron beam as shown above. Which of the following best describes the orientation of the compass needle due to the beam? So as we were talking in class, we want to go ahead and use the right-hand rule to determine the direction of the magnetic field around a beam. So what we have found out is that if you point your thumb along the direction of the current, then the curl of your fingers will show you the direction for the curl of the magnetic field. Now here we have electrons moving from left to right, which means that technically the current is moving from right to left. And it's okay, either way, that won't change the answer here for this question. But if we grab our fingers around the beam here, we're going to see our fingers curling around to the back of the beam here, such that if I were to try to break it up into sections, we would see the magnetic field pointing like this, curling around the beam with our right hand in this fashion. So let's go ahead and see here which of these compasses will work best. Well, immediately next to the compass, we have a magnetic field that is pointing in this direction. Now, if we look at this, the important thing is that these needles for the compass are going to align themselves with the magnetic field. Now, if we look at the magnetic fields go from north to south, which means that technically this is the north side. Now, their diagram here is not exactly correct. Our best answer choice here is D, but in reality, the colored arrow side, or the colored side, should be pointing in this direction. Because the compass points it actually to, even though we say it points to geographic north, that is the actual south pole of the magnet that represents the Earth's magnetic field. So in reality, it should be pointing towards the southern end, but it doesn't really matter because we only have one compass here that is horizontally oriented. And so this is the best picture. Let's go to the next one. The compass is removed and replaced by a bar magnet that is placed directly below the electron beam as shown above. In what direction will the electron beam spot initially move? So we've seen here, we have a magnetic field that comes out of the north side of a magnet. And so locally, this electron beam is feeling a magnetic field or experiencing a magnetic field directed locally up. Now we have to be careful. We've talked about how to determine the magnetic force because we're going to see the beam move in the direction of the force. The magnetic force is given by QV crossed into B. So we need to use the right-hand rule to determine this. And because this electron here is negative, we'll need to flip the direction at the end. So one way to think about it is I have my velocity from the side view in this direction. And then we have the magnetic field pointing up. We point our fingers along the screen, or along the velocity. We curl our fingers in the direction of the magnetic field. And what we find out is that the thumb is out of the page for positive charge from this perspective. okay? Which means that in this case, I have a velocity. We could even do physics gang with our pointer finger coming at us. We turn our fingers are such that our middle finger points up, and then our thumb is going to point in this situation out this way, which is consistent with the idea of this diagram here. Here, the magnetic force is going to be pointing out this way as the charge moves that way for a positive charge. But because this is an electron, we have to flip the direction. And what we find out is that the magnetic force here is going to be to the right on our electron beam. Go to the next question. This time, a wire is placed under the CRT, parallel to the electron beam. When a current through the wire is turned on, the beam spot changes position. Which of the following information is needed to determine the direction of the current in the wire? So we have seen that wires can carry current. So that's this guy. What they're telling us is based off of our first diagram, they placed a current carrying wire here, and they want to see which way this electron beam spot is going to move. Is it going to move up? Is it going to move down? Is it going to move to the stage right or stage left? And so if we look at this, which of these is needed to determine the current? Well, the length is not going to be needed because we're looking for directions. So chances are the distance that the spot moves can be used for calculations, but what we really need is the direction in which the spot moves. We find out that the spot moves to the right. That tells us that the magnetic field was pointing up in this direction. If it points to the left, then that tells us that the beam was moving to the, or create a magnetic field below it. So we need the direction. Question number 4. A plasma is a very hot gas comprised of freely moving positive and negative subatomic particles that are in random motion. Which of the following microscopic properties together allow a magnetic field to have an observable macroscopic effect on the plasma when the plasma is placed in a region that contains the magnetic field? We're going to choose 2 answers. So we're looking for macroscopic properties that allow us to see macroscopic effects. Basically, we can see things move. And so the particles have subatomically small dimensions? Not necessarily. We've seen that for, excuse me, sorry, like a mustache got in my hair, in my mouth. So if we look at this, magnets have a noticeable effect and they're not microscopic. That's not a property we're looking at. The particles are charged. It's going to be a big one. Charge is a microscopic property. So I think charge is one of our better answers. C, the particles are not all classified as fundamental particles. No, that has nothing to do with it. If anything, all fundamental particles, except the neutron basically, are susceptible, and even the neutron can experience magnetic effects, but we're not going to worry about that. And so the other one is that the particles are in random motion. We have guys moving all over William-Nillium, and all of a sudden we notice that they're all moving in a certain direction, then that will tell us that we had a magnetic field that caused this alignment. Question 5. Which of the following systems have a microscopic property of matter that allows an external magnetic field to cause an observable macroscopic effect? So if we look at this, that is going to be the iron filings that align themselves to the field, and the plasma is a very hot gas that has randomly moving particles. So these are the best ones. The other objects here do not have a noticeable charge or metallic property, magnetic property for us to take advantage of. Water does have magnetic properties, but we're not going to worry about that right now. That'll actually be next review session. A student uses filings to map the magnetic field in the space around a typical bar magnet. Which of the following diagrams best represents the orientation of the filings? So what we find out is that they're going to align themselves with the magnetic field, and magnetic field lines are going to go from north to south. And now we don't know which is the north end and which is the south end, but the important thing here is to recognize that when you have a dipole, the fields curl in on themselves, and a magnet and magnetic fields are dipolar, as opposed to monopoles like electric charge. Okay. Go to number 7. In the figure above, we see some field lines produced by an object that is just below the figure, but it is not shown. Which of the following could be the object that is responsible for the field lines that are shown? So we have said that field lines, magnetic field lines, point from north to south, which means that if we look at all of these fields, this has to be the north end because things are pointing out. And the fields curl in on themselves, which is indicative of some kind of dipolar situation. We need a north and a south pole. So a bar magnet with its north pole pointing up, that sounds about it. Let's see here, B. A bar magnet with its north pole pointing to the left, no. A magnetic monopole, as far as we know, those do not exist. So A is our best answer choice. If these magnetic field lines happen to radiate away from the north end and they told us that this was a magnet, then maybe we could go with C. But that's not the case. As far as we know, we do not have monopoles in magnetism. So it is very common to see or ask, well, if we take a magnet, we cut it smack dab in the middle, can I have a pure north pole and a pure south pole? And the answer is no, sorry, it won't work that way. And it's not, and so the idea here is, well, what if we cut it into 3 pieces then, right? What will happen? Because if I cut it into 2, and I'm just doing this dashed line here to represent the difference in poles, that would form a south pole, and we would get a north pole on this end. But what if we cut it into 3 pieces? What would that look like? So we'll cut it into 3. And I'll do dotted lines to separate the poles. But each solid line is a cut in our magnet. So what we find out is that we have a conservation of field, if you will. So our best answer choice is going to be C. Out of these 2, or out of these 4, these 2 can be eliminated, A and D. We're not going to get no magnetic field here, okay, or magnetism, period. This just doesn't happen. Oops. So you can't just cut a magnet and lose its magnetic properties. They got to be conserved. And so as we separate these, just like when we did it with 2, we ended up with a south end over here and a north end here. You can kind of think of it as, okay, if these guys were stuck together, how would they stick? Oh, well, they got to connect north to south, if you will. And so C is our best answer choice. Let's go to number 9. 4 charged particles are moving directly above or below a horizontal current carrying conductor that is at the instant shown above. The signs of the charges and direction of motion of the charges are indicated in the figure. Particle A is moving horizontally out of the page. Particle B is moving vertically upward. Particle C is moving horizontally into the page, and particle D is moving horizontally to the right. Which 2 particles will not experience a magnetic force at this instant? We're going to select 2 answer choices. So if we remember, we said that a current carrying wire has a magnetic field wrapped around it. And so we grab it with our right hand and we curl our fingers such that our thumb sticks out and points in the direction of the current. When we do this, if I look at my fingers at the top of the wire, I see my fingers coming out towards me. The fingers are pointing out of the page. So the magnetic field here at the top is going to be out of the page, which makes the bottom of the wire have an into the page magnetic field. As we curl around and roll our fingers around, we notice that they're pointing away from us on the bottom of the curl, which means that the magnetic field vector is pointing away from us or into the page. The other thing we said is that the magnetic force FB requires, or M, sorry, they usually use M in the College Board. The magnetic force requires V to be perpendicular to B, which means if V is parallel to B, then the magnetic force is going to be 0. So we need to find scenarios where these charges have velocities that are parallel to the magnetic field. So if we look, particle A has a velocity that is coming out of the page and is parallel to the magnetic field. So the magnetic force for this individual is a big old 0. So A is one of the particles that will not feel a magnetic force because it is not moving perpendicular to the field. If we look at another particle, well, B is perpendicular to the magnetic field, so not this guy. C has a velocity that is into the page, and the field, the magnetic field specifically, for that charge, or for this wire, sorry, is into the page. So this guy's also parallel to the field. So C will also not feel a magnetic field here, or a magnetic force. Question 10. A cathode ray tube uses a stream of particles to create a spot on a screen. Students are asked to design an experiment to show that the particles in the stream are charged and to determine the sign of the charge. Which of the following procedures will best accomplish the objective of the experiment? So, going back to question number 1, where we had our cathode ray tube, a cathode ray tube is going to be shooting electrons in a direction such that the beam is going to strike some kind of screen to detect the position of the strike. And we can put magnets and capacitors around the screen to change the magnetic and the electric field to influence the path of the beam. So here we need to determine the charge of the sign of the charge and to see their charge. Bring a neutral conducting rod near the stream to see if the beam is deflected. If so, observing the direction of deflection. So that's not really going to help us here. So if we have a neutral item, there's no charge, there's no influence. So we don't really want to look at A or B here. C. And on top of that, it's separated by gas. A vacuum, and then glass. So it's not like the charge is going to deposit onto the beam here. It's separated by an insulator. C, bring a wire with a known current near the stream to see if the beam is deflected. If so, by observing the direction of the deflection. C looks pretty good. D, bring a wire with a known current near the stream to see if the spot on the screen changes size. That's not really going to do anything. We're looking for the direction of the force. And so if all these particles are moving in one direction and the magnetic field is in one direction, all those particles are going to feel a force in that given direction. They're not going to disperse. They're all going to move relatively in unison as a group. So the spot will change position, but not size. Go ahead and look at number 11. In the experimental setup shown above, a charged particle is initially moving to the right and then passes through two regions. In region A, there is a uniform magnetic field directed into the page, and so we see the axis. In region B, there is a wire in the plane of the page that carries a current, and the magnetic field caused by the current only has a significant magnitude in region B. So the effect or the magnetic field from the current on in the wire is negligible once we are outside region B. The particle is deflected toward the top of the page in region A and toward the bottom in region B. What is the sign of the charge of the particle and the direction of the current in the wire? So let's see here. So we have to play that game that we were doing in class today. We have a velocity in this direction, and we'll do the right-hand rule to see the direction for the force in on a positive charge. And if that is the case, then we know that this is positive. If it is in the opposite direction of the right-hand rule, well, then we know that it's the opposite charge, a negative. So let's see here. We point our fingers along B, so to the right. Our magnetic field happens to point into the page, so we have our finger pointing towards the screen or into the page. And what we find out is that if Q is positive, the magnetic force is directed upwards. And they told us that it's going to deflect towards the top of region A. So it looks to me like the charge here is positive. Now, let's go ahead and put the next point in here. The next part is they tell us that when it's in region B, it will be accelerated toward the bottom region or the bottom of the page in region B. So here, when we grab our wire, we can already kind of assume, okay, we have a velocity kind of in this direction. It's not perfectly horizontal, but maybe, we can go ahead and still say, you know what, it didn't finish making a turn. So it's coming in like this. So if we look, our field is either going to be pointing out of the page or into the page for our current. So we'll take it one at a time. Let's say the current is acting up or pointing up. Well, we grab the wire with our hand, metaphorically, and we wrap our fingers around. And so let's see here. This would be out of the page here, and it would be out of the page everywhere on the left-hand side of the wire. This would be the magnetic field created if this current was pointing up. Well, let's go ahead and do the right-hand rule here. And so if we notice, we go ahead and put our fingers kind of along B, which is kind of at an angle, and then we curl our fingers out of the page, and what we notice is our thumb points down. And because this is a positive charge, we don't need to flip the sign at the end. We can go ahead and say, oh, okay. We can go ahead and say that the magnetic force is pointing down, or a field pointing out of the page on the left side of the wire, which is consistent with a current acting toward the top of the page. So answer choice A is our best answer. Now let me know if we have any questions. My brush got messed up. Okay, looks like we don't have any questions. Let's go ahead and continue. An object with a net charge of 10 millicoulombs, positive, moves with a speed of 20 meters per second through a magnetic field of magnitude of 5 teslas. The force exerted on the charge by the field is 50 or 0.5 newtons. And the question is, what is the angle between the object's velocity and field? So let's see here. So we have learned that the magnetic force is given by Q, V, B with a cross product. Or we can go ahead and use the vector form or the non-vector form of the cross product, which uses the angle Q, V, B magnitudes times sine of theta. And that's kind of what we're looking for here. So we know the force from the magnetic field, we know the value of the magnetic field, and we know the magnitude of the velocity as well. So we can go ahead and say sine of theta is going to be the magnetic force all over QVB. So that becomes 0.5 newtons. Q is going to be 10 times 10 to the negative 3 newtons, sorry, coulombs. The velocity happens to be 20, and this is 5 teslas. Automatically, this makes 100, or 10 to the 2. And then this is 10 to the negative 3, so we have 10 to the negative 1, all over 5 times 10 to the negative 1. I feel like I did that right. You know what? Let me just make sure I did that correct, because I feel like that's positive 1. No. Anyways, let's do it. 10 e to the negative 3 Oh, but that's 10. So that's really okay. Okay. Yeah. 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 And then 20 multiply and then 5 multiply. Yeah. That's really a 1. 10 to the negative 1, which is really, and it doesn't matter. Hopefully we see that this is 1 times 10 to the 1. This is, sorry, I'm fumbling here. This becomes 0.5 over 1. Or sine of theta is zero point 0.5. Man, I really struggle with that. Even though I could see it, like I really sucked at explaining that. Where are the numbers sense here? The Ghostbusters Cumbia. I didn't even know this song existed. Sorry. Just listen to music in the background. Thank you. I appreciate that. Alrighty, 13. At a particular instant, a positively charged particle is moving parallel to and in the same direction as the current in a long straight wire. In what direction, if any, will the charge be deflected? So they don't give us directions here, but they kind of use the directions relative to the wire. So let's go ahead and draw a little wire. And we're going to define the direction to be to the right because it's easiest to work like that generally. If we grab the wire with our right hand, our thumb points along the direction of the current, and our fingers are going to wrap around the wire over the top and come out of the page at the top, and the magnetic field will be pointing into the page on the bottom. And they tell us that a positively charged particle is moving parallel and in the same direction of the current. So let's go ahead and say I have a little proton moving in this direction. So if we look at this, we have a velocity and we need to do QVB. We do the right-hand rule again. We point our index finger to the right. We need to rotate our wrist so that, and you may need to stick your hand out to the side. And that's kind of like one of the detriments of the right-hand rule like this. And you're going to have to point your middle finger out of the page. And what we find out is that the magnetic field in this direction points downward or toward the wire. Now, my concern is, well, what if it's on the bottom, right? Because here I happen to have downward and it looked towards the wire. Let's say I have this positively charged particle moving in the same direction as the current on the bottom. So we do the right-hand rule again, and we point our finger to the right. In this case, we point our index finger again into the page, and our thumb happens to tell us that the magnetic field is going to be pointing up. And so this positive particle will move in that direction, up, locally up, or towards the wire. Let's go to number 14. So here we have a coordinate system defined for us. If you take your right-hand rule, you point your fingers along X and then Y, X into Y creates positive Z, and positive Z is going to be pointing out of the page. You could do the curl method. You take your fingers and you point them along X, you curl them in the direction of Y, aka up, and your thumb still points out of the page. A wire parallel to the Z axis carries current in the figure shown above. The table above shows the data indicating the direction of the force exerted on a charged object. Come on. When it's starting to act up. Indicating the direction of the force on a charged object moving in different directions near the wire. A charged object is positioned above the wire in the XY plane when the direction of the force is recorded. So we're going to have some kind of object up here. What additional information, if any, is needed to determine whether the current is in the positive X or negative X direction? So let's see here. So let's see. When our object happens to move parallel to the x-axis, so let's say we have a velocity in this direction. We know that, oh my God, there's a Pokemon Cumbia too. When it moves to the in the positive x direction, the force happens to be in the negative y direction, which hopefully we're thinking, hey, we just kind of saw an example like that. Yeah, here, if you want to, let me do a new screen share. No, I don't know if I should share. Or not a new screen share, but just like the audio. So, as you guys have kind of heard, oh no, it's not. This is the Kirby theme, actually. Anyways, yeah. So there's like a music genre called cumbias, and sometimes I'll listen to them, and you'll hear random remixes of like songs. And so this was the Kirby theme song, or not the theme song, but the Woods. I don't know, whatever. William, someone's about to spawn in storms with Kirby facts. I think I know which student we're talking about, but let's proceed. Yeah, yeah. I did not know they were a big Kirby fan. So if we look at our example before, when this thing was moving in the positive x direction and the current was moving in the same direction, the magnetic force was down. So we should probably have a hunch that, okay, the current is probably moving in this direction. Let's go ahead and look at when we move parallel to the y direction. So if I have a velocity in this direction, we throw our finger up, we point our finger, and we know that the direction of the force is in the positive x direction. So what we know is that in this case, the force, aka our thumb, is going to point in the positive x direction, which leaves our middle finger, which represents the direction of the magnetic field, to point out of the page. And they did tell us that it is a positively charged particle, right? Like I don't even think they told us this actually. Oh, okay. I see what we're going. I see what we're thinking. Or I see where they're going with this. Sorry. So if it moves in the z direction, then it's parallel to the magnetic field and there is no force. Okay, so that makes perfect sense. So what do we need to finally figure out the direction of the current? We need to find out if this guy is positive or negatively charged. So we only need the sign of the object's charge. So the rest of these, we are only the direction of the motion of the object along each axis is indicated. We don't need that. Both the sign and the direction of motion. So we don't need the direction of motion because what we're concerned with is with this kind of thought process, we need the force, or these directions are only for velocity, magnetic field direction, and the force direction. So we don't actually need to know which way uh, the motion is directed because we already have these directions of motion. So A is the best choice. Let's go to number 15. Each picture choice, we probably didn't need to spend that much time on that question, sorry. But let's proceed. Each picture choice below represents a close-up view of magnetic domains in 4 different magnets. The arrows represent the net magnetic fields of the individual domains. Which of the magnets have a significant magnetic field? Select 2 answer choices. You could actually close Spotify. Alrighty. So if we look at this, we need to try to find a net magnetic field. Oh, no. Okay. No, I just figured, like, yeah, it gets a little hard because we may be thinking, let's count these. So by inspection, we have a general upward direction for all of the domains in D. So D is a pretty good one. Now, this can be a little annoying. We have 3 pointing in this direction. We have 4 pointing, or 3 pointing in that direction as well, generally speaking. This one doesn't have a very noticeable direction. So I'm going to say it looks like here all of these guys cancel out. If we look at scenario A, we don't really see any downward arrows. Sure, we have cancellation in the horizontal direction for the domain directions, but overall there is a net magnetic field that we can go ahead and say is noticeable in the upward direction. A student is comparing the fields created by two objects. The gravitational field, no, you're good. The gravitational field of a very small sphere and the magnetic field of a magnetic dipole. Okay, a student is comparing the fields created by two objects. One of the objects and the fields is the gravitational field of a very small sphere and the magnetic field of a magnetic dipole. Which of the following statements are true for the magnetic dipole's field, but not the sphere's field? Okay. So they want us to find is true for the magnetic dipole's field, but not the sphere's field. So if we look at the gravitational field of a sphere, these guys are radially inward. And the gravitational field strength is represented by the density of the arrows such that the grouping is much closer to the object and much weaker as we get further apart. For a dipole, let's say I have some north, I'll go ahead and flip the magnet here, and I have the south, the fields go from north to south. So let's go ahead and see here. The vector fields are always radial. This is not true. This is true, or this is not correct. This is true for G fields and electric fields. These are monopoles. But this is not true for dipoles, which is what the magnetic field is. There are two poles to a magnet. B, the field exists everywhere in space around the object. That's true for both. And these fields tend towards infinity, but they will still be some existent value infinitely far, well, to large distances unless we're infinitely far away. If we remember, the definition for B for a simple wire is given by mu naught I over 2 pi r. So it's only at infinity that we do not have a magnetic field. The magnetic field is small at locations very far from the object. That will be true for both of them. Kind of like it's kind of like the same statement as B. The fields exist everywhere in space around the object except at very far distances. So that leaves us with D. In some regions, the field points towards the object. In some regions, the field points away. At the bottom over here, it's pointing away from the object. As we start to loop around, it points into the object, into the south end. The magnetic field only ever points towards the object. Sorry, the gravitational field only ever points towards the object. Let's go to 17. A particle of mass m naught and charge positive q naught travels in the direction shown above with a speed v naught such that the particle is at the midpoint between two identical magnets of mass m. Which of the following indicates the direction, if any, of the net gravitational field B from the magnets and the direction, if any, of the net magnetic field at the particle's location? Zoom out a little bit so we can see it all. Alrighty, we'll go ahead and start talking about it, but you can go ahead and continue working. So if we look at the scenario, the gravitational field for these magnets is going to be pointing inward. That's going to be the gravitational field. Now, both of these have gravitational fields pointing inward to them. And if they have the same mass and we are smack dab in the middle, the gravitational fields are going to cancel. It's kind of like if I'm between two planets of the same mass, if I'm smack dab in the middle, I'm not going to go anywhere because I have equal amounts of mass attracting me in both directions. If I'm at the center of the earth, I feel no gravitational force because the mass of the earth is pulling me in all directions. So the gravitational field will be no direction. Now let's go ahead and talk about the magnetic field. Well, the magnetic field points away from north and points towards south. So we're going to have a net direction to the left for the magnetic field. There we go. All right. We're technically done for today. There are a couple of questions here that kind of apply with today's lesson. They're part of the next multiple choice question set. And so it's only about 2. So let's go ahead and, if you want, we can take a look at this. If not, yeah, when I saw your choices, like, I think yeah, the title of the column got mixed there. All righty. Let's go ahead and look at the next one. Okay, no worries. All righty, I'll rush through these. So we have a proton traveling horizontally with a speed of v, and it enters a region of a uniform magnetic field of magnitude b directed into the page, and a uniform electric field in the direction up. So this is the direction for the magnetic field. This is the direction for the electric field. And the question is, which of the following free body diagrams represents the forces exerted on the proton immediately after it enters the region? So it hadn't been feeling any force. All of a sudden, it crosses into a region where both of these are. In a meeting at 7? Shoot. All right. I'm trying to get the scroll just right. Okay, let's go ahead and tackle the electric field first. So we have learned that the electric force is given by Q times E. And because the electric field is a vector and the force is a vector, basically the direction is determined by the electric field for a positive charge, which is the case here. We have a proton. So if we see here, these arrows always represent what would an electron do. So it's going to feel an electric force in the upward direction because it's a proton. Now we need to do the right-hand rule for the magnetic force. So we have a force in the x, a magnetic field in negative z. We should be expecting a force in the y direction. Nah, I wouldn't doubt yourself. You're pretty legit, dude. I don't know. That was like a phrase, or I don't know, like a pressure. Anyways, I'm sorry. We have like 3 minutes. Okay, so we do our right-hand rule. V goes to the right. B points into the page. The force is up. So it turns out both of these are in the. Yeah, I do. Right. I think we all agree with that. Absolute shame. But yeah, I was gonna say, but not because I'm sorry. So a bunch of them go into that to fight the stereotype, but like not because they want to. I see. Well, I mean, ultimately, hopefully it's a thing of passion, because when things get really tough and boring, Okay, it's not like not because of a genuine interest. Okay, I got you. A sense of pride. I mean, that is still a sense of pride. But I guess what I have found is that when you have a passion or an interest in it, it's a little easier to roll with the punches. I know, like for instance, I wasn't very particularly capable in math and science at the beginning. I mean, science to an extent, but physics wrecked me. But it was just one of those that I kept at it because I liked it, and here we are. Yeah, they're interesting, but if you like getting hit in the face and be like, oh yes, this is neat, this is cool, we've learned, there's something for that. Question 6, let's go ahead and take a look over, yeah, um, real quick. All right, so let's see here. A positive charge is momentarily at rest in a region with an electric field directed upward and a magnetic field directed to the left. So we have a couple of fields here acting on this bad boy. And it's represented by a dash line for the magnetic field. In what direction is the net force on the positive charge at this instant? So if we look at the electric field force, that's Q times E. Okay, there's an electric field, there's a charge, and that force is going to be upward because this is a positive charge. It's going to move in the direction of the field. Now, when we look at the magnetic field, that's going to be Q, V crossed into B. And they told us that this charge is momentarily at rest. So at the very beginning, V original is 0, which tells us that the magnetic field is equal to 0. So it turns out that at the very beginning, the acceleration and the net force of this particle is going to be straight up. Once it begins to gain velocity upward, it's going to start to curve due to the magnetic field actually creating a force once it's moving. But initially, no velocity, no magnetic field. Question 11. In a region with no external magnetic field, an electron creates a magnetic field in the space around the electron itself. Which of the following statements justifies the claim that the electron will not be deflected by its own magnetic field? So really important. This is one of those, an object cannot push against itself. It cannot act on itself. There's a principle of no self-action. If I push myself, I cannot push myself to move. The moment I push on my chest pushes back with an equal and opposite force, and those two forces cancel out. They are internal to my system, and this is why we keep stressing the idea that we are looking for the net force that acts externally on the system or the object. And so an object cannot push itself. Very important. All right, we'll go ahead and call it here. Thank you for attending. Take it easy and have a good afternoon. We'll see you guys tomorrow for another review session since Physics 1 will be over.